Hello and welcome to video 2. In this video we're going to cover how OFDMA works and some OFDMA frame exchange processes, both downlink and uplink. Since these are the only two areas we're going to cover in this video, we're going to go through them quite extensively. Let's get started. The first section will be about how OFDMA works, starting with kind of a high level and then working our way into more details. Previous PHYs from 11B, A, G, N, and AC all use a single lane as an analogy. They can only have one transmitter on the channel at a time. So they must compete for a transmit opportunity, and then the winner will transmit and hopefully be successful, but no other transmitters can transmit at that time. So it acts like a single lane highway, and no matter how fast or how slow the transmitter is going, everyone waits in line behind it. 11AX, with a focus on efficiency, works as a flexible mini lane highway. And effectively, the access point acts as the traffic cop. So as you can see in the graphic at the bottom, we have multiple lanes where we have bicycles and motorcycles, and we have forklifts and cars and large trucks and medium-sized trucks and so on. So on a 20 megahertz wide channel, an access point can have up to 9 simultaneous downlink transmissions and or uplink transmissions as a maximum. I've only drawn 4 lanes here just for space on the slide, but the point is that the lanes can vary in width. These lanes are called resource units in 802.11ax terminology, and they are determined, the width of these transmissions are determined by the access point, either for uplink or downlink. Multiple clients can transmit uplink to the AP at a time, and the AP can transmit downlink to many clients at a time, up to 9 on a 20 megahertz channel, 18 on a 40 meg channel, and 37 on an 80 meg channel at a time. Of course, more simultaneous transmissions mean more calculations for the CPU and would become increasingly difficult for calculations, but that's another topic for another slide. Transmissions can be either uplink or downlink, but you can't have both at the same time during the same tick-sop. Once an access point wins access to the medium, it can transmit downlink to multiple clients or cause multiple clients to transmit uplink at a time. And the multiple simultaneous transmissions that are not in contention with each other because they're in different resource units or different lanes, if you will, is what drives the efficiency of 11AX. This slide gives us a comparison of the different physical layers starting with 11N. We'll work our way from top to bottom. The channel size with 11N was either 20 or 40 megahertz wide, whereas 11AC would give us 80, 80 plus 80, and 160 as an additional channel widths. 11AX is unchanged from 11AC on channel width support. Subcarrier spacing has been 312.5 kilohertz wide on a OFDM since 11A, and of course through 11G, 11N, and so on. And now 11AC adopted the same, but 11AX, in order to subdivide the channels into more granular subcarriers, has divided them by 4 into 78.125 kilohertz. This allows us to create granular resource units that we will use as a flexible mini lane highway, if you will. The symbol time is the time that is used on each subcarrier when transmitting to transmit the data. So they've been a maximum of 4 microseconds for 11N, 11AC, but now a maximum of 16 microseconds for added efficiency. We'll cover that on another slide. The frequency multiplexing options here have been OFDM since 11A, and of course with 11N we adopted HT OFDM as well, high throughput OFDM, which is a more efficient version. 11AC also supported OFDM and HT OFDM, and now 11AX supports both of the same plus the new OFDMA physical layer. So we have now 3 options. OFDMA as will function during a tick-sop, but of course 11AX access points can talk to 11AC, 11N, 11A, and 11G clients with OFDM and HT-OFDM. So fully backwards compatible. Modulation support with 11N was maximum of 64 QAM, and then 11AC extended that to 256 QAM with 8 bits per symbol instead of just a maximum of 6. And now 11AX adds a new option for 1024 QAM, giving us 10 bits per symbol, so more efficient transmission, but requiring about 35 dB of SNR to be successful. Multi-user MIMO was not available with 11N, but with 11AC was available as a downlink variant. In 11AX, we will have the capability of both uplink and downlink variants, but we don't have high expectations for this in the enterprise. Certainly it has its use cases in homes and small businesses and things like this, but with lots of clients that are constantly moving, there are some challenges with multi-user MIMO, giving the benefit that it promises in marketing literature. The spectrum bands supported by 11N are both bands, 2, 4, and 5 gig, whereas 11AC only supported 5 gig. Well, 11AX is now back to supporting both bands, though we don't have high hopes for 11AX in 2.4 gig because of the vast number of legacy devices and interference sources. And of course, often we see the 2.4 band is very dirty and very busy due to these problems. So certainly most implementations in the enterprise of 11AX are going to focus around the 5 gig for maximum benefit. What we've traditionally called subcarriers, we're now calling tones. Subcarrier spacing is 312.5 kilohertz wide, and there are 64 within a 20 megahertz wide channel with OFDM and HT-OFDM. With 11AX, we have divided the width of the subcarriers by 4, yielding a 78.125 kilohertz width and 256 tones per 20 megahertz wide channel. This division by 4 of the width of the tones from the subcarriers is going to allow us to create granular resource units, as we'll see on the next slide, in groups of 26, 52, 106, or 242 tones per group or resource unit. As we can see on this slide, we have various widths of resource units. You can see starting from the top 26 tone RUs, and in the middle there you've got a pair of 13s that will act as a single 26. You've got 52 tone RUs, 106 tone, and 242 tone. The 242 tone resource unit is the entire channel width. So that would be when an access point or a client is using the entire channel for the purpose of a high data rate and hopefully high throughput transmission. Of course, that would also take into consideration there's probably no other clients connected if the AP is constantly allocating 242, or it could be that it's a very short-lived, single tick-sop out of many scenario where a client is trying to move lots of data very quickly, and the access point is trying to allow that client to move that data by allocating the entire channel periodically to it. Now, these groupings or resource units of tones like this can be in various combinations. We could have 926s, 452s, 2 106s, or a 242, but then we can have all types of combinations. We might have, for example, 326s and 352s, or a 106 and 252s, or something like this. So the access point is going to size and allocate the resource units to clients depending on the client specs, the SNR, as well as the application that is flowing either to or from those clients. Access points will query the buffers of the clients to see what type of traffic and how much of that traffic is queued for uplink transmission, and will assign, of course, the resource units accordingly. So the 20 megahertz channels are broken down into these resource units, and it's a matter of type of trivia, really, that a 26 tone RU is about 2 megahertz wide, whereas 52 tones is about 4 megahertz wide, and 106 tones is about 8 megahertz wide. The purpose in explaining that is to help you understand that from a previous slide we talked about efficiency gains as we went from 80 to 40 to 20 megahertz channel widths, and now you can see that we're breaking them down into dynamic flexible channel widths of about 8, 4, and 2 megahertz in order to assign only as much as needed to particular clients for the applications that they're running. So the resource units are allocated to the clients, either uplink or downlink, on a per TICS-op basis, meaning the access point has to win a transmit opportunity and then decide does it want to transmit downlink or cause the clients to transmit uplink. The resource units can only be assigned to one user, and of course that user can only be assigned to one resource unit, no matter the width. You cannot assign, let's say for example, a 52 and a 106 to a particular client. Downlink and uplink OFDMA, which is a multi-user scenario, may be combined with uplink and or downlink multi-user MIMO. Now, we're not particularly concerned with multi-user MIMO at this point, as it's not done a lot for us in 11AC, and we don't have high expectations in 11AX. But downlink and uplink OFDMA as a type of multi-user scenario with these multiple lanes, multiple transmissions at a time, is the core technology of 11AX, and that's something we should be hyper-focused on. This slide goes right to the heart of what OFDMA is. This is where the access point is assigning the resource units to the clients for uplink or downlink transmission, up to 9 clients per 20 megahertz wide channel. Now you can see that starting on the left side, we have one color that is representing one client assigned to the entire 242 tones, the entire channel, if you will. In the next TICS-op, we have 4 colors, so that might, for example, represent 4 52-tone transmissions, whereas the next one's 242, and maybe the next with 2 colors, as you can see, are green and red. That might represent 2 106s, followed by another 242, followed by 2 52s and a 106, or something along those lines. So the purpose here is to understand that the access point is assigning a certain number of tones in a group called an RU. So it's assigning a width of RU per client for transmission or reception, depending on if it's downlink or uplink. Now, how does the access point know how to assign properly resource units for clients to transmit uplink? It does this by buffer sounding. There's a sounding process, which we'll cover a little bit later, where the access point simply asks the clients for their buffer depths, that is, what is in your queue and how much is there. And so that way it can assign a proper RU width for each of those clients on a per TICS-op basis. Here we can see in the upper left quadrant, the blue and white chart, you can see that in a 20 megahertz wide channel, we can have up to 9 resource units assigned. And of course, if there were 9, they would be 26 tones each. That's the most granular assignment possible. Using that same 26 tone RU scenario, in a 40 megahertz wide channel, we could have 18 resource units and then 37 on an 80 megahertz wide channel. Now, we typically don't go any further than that in most implementations, so I'll stop there. But of course, if we went to 52, those would change to 4 and 8 and 16 and so on. And we have the possibility of many combinations where we can have so many 26s and so many 52s and all that in combination. So there's a lot of variety that's possible for the AP to assign. And you can see over on the right side, top to bottom, a 20 megahertz, 40 megahertz, and then 80 megahertz channel, and where we have the resource units are shown in green, and then we've got some of the tones, or in this case subcarriers, shown in between them in yellow, or in the middle it says 7 DC, for example, is 7 direct conversion. That means it denotes the center of the channel using 7 tones. And you can see in these graphics, they've got the pilot tones where they are from center. Center is considered 0, and then we go out negative to the left and positive to the right from there. So these graphics simply show where the usable resource units groupings are, where the unused tones are on the edges and in the centers, and then where the palette tones are. It's important to understand that 11AX is not holistically deterministic. And what I mean by that is it is not in control of all the clients all the time. It's only going to be in control of the 11AX clients, and it will only control them during a TIX-op. So it has to win a transmission opportunity. So the underlying functionality of 11AX is still EDCA. In other words, it's still an overall competition. The efficiency gain comes with 11AX clients being able to be controlled uplink and downlink during the AP's TIX-op. So that definitely does add efficiency, but it still has to be backwards compatible, competing under the rules of EDCA. As you can see on the left, I've added an illustration from a video game from the 80s called Dragon's Lair, and you can see that the knight is hitting the squares on the floor and assigning different widths that our hero Dirk has to jump around. So that's essentially a pretty good graphical representation of what's happening here as the AP is assigning these RUs to various clients. It's very dynamic, it's fluid on a per TIX-op basis. Now on the right side, we've got a giant intersection. This represents EDCA. It's still a free-for-all. It's still a competition. The only real difference here would be if we had a large bus going through. So once the bus figured out how to get through the intersection, it would take lots of clients with it, uplink or downlink. And so it would be a limited determinism within EDCA. Something to take away from this is that the access point, in order to win a TIX-op, still has to compete against all of the legacy clients as well as any neighbors that are on the same channel. So this means that the less legacy clients and nearby APs that you have, the more deterministic the medium gets, and the more benefit and efficiency and throughput and system-wide throughput and per client throughput that you're driving. So it becomes more important than ever to replace your clients with 11AX. This slide gives us an example of an AP allocating resource units to stations or client devices. In the beginning, the access point will have to arbitrate for a TIX-op, as you can see, AIFS, arbitration interframe space. And then once it wins the TIX-op, it will send a downlink trigger frame that will assign the resource units to each station. Then, once they've been assigned, the stations will transmit uplink. As you can see, the station number 1 has a 52 tone, station 2 a 52 tone, and station 3 a 106 tone. And which subcarriers or tones that they're using is also assigned. And then, of course, the access point will have to acknowledge those 3 transmissions, and it will do so with a multi-station block ACK. That would be a 20 megahertz wide transmission that all of the clients could understand, and it will, of course, have the frame numbers in it so that the stations know that their transmissions were received properly. Here's what those assignments would look like just in a simple chart. You can see that from the same from the last slide, we've got 2 52s and a 106, and we've assigned RU number 1 is a 52 tone from subcarrier -121 to -70. And then you can see that RU2 is -68 to -17. Now 0 is in the middle of the channel, so to the left of center will be negative, and to the right of center will be positive. So we can see that, again, RU number 2 on the right for 106 tone, so if we had both 106, it would be RU1 and 2, but this is RU2 for 106 tone is from 17 to 122. And so this is how the trigger frame would allocate at both the physical and the MAC layer, would allocate these RUs to the clients, causing them to then transmit uplink after a CIFS. Now let's talk about some terminology for multi-user. I alluded to this earlier, but I wanted to clarify here. There's 2 types of multi-user within 11AX. The very definition of multi-user means that there's transmissions can occur between an AP and multiple clients simultaneously, whether it be uplink or downlink. And 11AX supports OFDMA, which is kind of the heart of the core of the 11AX PHY, and multi-user MIMO, uplink and downlink. So we have both of these types that are very different in how they function. Now, multi-user MIMO has already been available with 11AC, and it has very high overhead, very high complexity, and sometimes, depending on channel sounding, the number of clients, how much moving, and all the things like this, you could end up with a net loss. In other words, it's not an efficiency gain, it's just an efficiency loss. It all depends on the environment and the client support and the sounding and things like this. Also, OFDMA and multi-user MIMO can be used simultaneously. Not that we really would care to do this. I personally would want to turn off multi-user MIMO in most of my systems, but OFDMA is with 11AX clients is going to give us a pretty significant bang for buck in the long run. So this is a nice technology. Okay, this next section is about OFDMA frame exchange processes. We're going to get into the back and forths between APs and clients. On this slide, we have a downlink frame exchange process happening. So from the AP on the left, you can see the first thing would happen is it would have to arbitrate for the channel with AIFS. Then it's going to send a modified, most of the time it's going to use RTS CTS, so it's going to send a modified trigger frame called a multi-user RTS. And after a short interframe space, all of the clients will then send back up a CTS frame on their particular resource units. The resource units are assigned in the trigger frame, in the RTS, in the physical header, as well as MAC. Once the CTS frames are received by the access point, it's going to then transmit the downlink PPDUs, that is the data frames, downlink on each of the assigned RUs for those stations. Those stations, of course, know to be listening on those RUs because the trigger frame indicated that. After the data frames are transmitted, there will be a block ACK request after a CIFS, and then another CIFS. The stations will each transmit block ACKs on their assigned RUs. This slide simply uses text to walk through the same exchange as we saw on the last slide. We have a multi-user RTS, which is an extended trigger frame that's going to indicate to the stations which resource units to be listening on. And of course, the multi-user RTS is sent across the entire 20 megahertz wide channel. So all the legacy clients are going to understand it as well, and they're going to back off due to the duration fill value that is found in the RTS. Now, legacy clients won't understand the CTSs because they're going to be sent on the RUs on the uplink. The transmit opportunity is for the entire frame exchange as always. Now, this again, the CTSs are sent in parallel on their assigned RUs. Then the access point will send the PPDUs, which are the data frames, downlink. Now, you see it says DL downlink multi-user. That's OFDMA, not multi-user MIMO. So those transmissions will go downlink on their assigned RUs. And then we'll have a block ACK. Now, the block ACK can take two process variants. First, we can have the clients just automatically block ACK. As soon as they receive a data frame, especially if it's an A-MPDU, the standard allows for just automatic block ACKing. Or we could have a block ACK request from the AP followed by block ACKs on each of the RUs from as kind of an extended process. Now, it's important to note that the AP transmit power is adjusted per resource unit. And in fact, when it assigns for uplink transmissions, it can assign power levels to the clients as well, and many other parameters. This slide shows an uplink OFDMA frame exchange process. In order for the access point to understand how to assign the resource units to in each individual station, it needs to understand the buffer depths, the type of traffic, and the amount of traffic on each client that needs to be transmitted uplink. So the access point is going to send down a buffer status report poll that will solicit a buffer status report, or BSRs, from the stations to begin with. It has to understand what it needs to assign, so it needs to know what needs to be sent uplink. So we'll start from left to right. The access point arbitrates for the medium with AIFS. It will then send what we call a variant of the trigger frame, a BSRP, buffer status report poll. After a short interframe space, the stations will each send their buffer status reports, their BSRs, indicating how much traffic and what type of traffic are in their queues. Then we're going to send a second trigger frame variant, the multi-user RTS, as we saw before, and in the downlink process. And then that will, of course, trigger the 4 CTSs in this particular scenario in parallel on the resource units. Then the next trigger frame will be sent. Since this is uplink, we have to trigger the stations to transmit. So that trigger will assign the RUs to each station. Now, when we use the first trigger frame, the BSRP, we assigned usually a 26 tone for the BSR. So there's an assignment that happens in trigger 1 so that the BSRs come back up on the to the AP on specific RUs. But trigger number 3 assigns the new RUs for the clients to use for data. So those may vary from the BSRs. So we have the trigger number 3 that's going downlink, and then the stations will transmit back their data on their assigned RUs. An important and almost vital piece of information here is that the stations must transmit uplink for the exact same amount of time. Now that will be determined by the access point. And clients that have less data to transmit must add a pad so that they're constantly transmitting exactly the same amount of time as all the other stations. That pad is simply bogus data but that allows them to constantly transmit. And of course, they indicate that that's a pad information, but they are all required to transmit for the same length of time. They may be using different spatial streams, different modulation, and many other things, but they have to transmit for the same amount of time. And of course, after the AP has received the uplink transmissions, it will send a multi-station block ACK downlink across the entire 20 megahertz wide channel, indicating receipt of the PPDUs. It's also important to note that the buffer status reports can be sent by the clients without any preceding buffer status report polling. It can just simply gratuitously send its buffer status report uplink at any time. But this would be done so in another frame, and usually as part of the QoS control field in a data frame. So even if not asked, it could populate that control field, QoS control field, in a data frame just to indicate what it does currently have in the queue. Again, this is a textual walkthrough of the same thing we saw on the last slide. The process is simply the AP needs to know what the buffers look like on the client, so it sends a BSRP. The clients are going to reply with BSRs on their assigned RUs, which are assigned by the BSRP frame, which is a type of trigger frame. And of course, then part of that BSR is going to be information about their AID, the data link that they have to send, the type of data, which is the QoS level or access category they have to send, and so on. The AP is going to build its RU schedule and then send that down to the stations with start and stop times, which is they have to transmit for the same length of time, which clients will be on which RUs, and their MCS settings, the power levels per RU, and so on. So they're very specific in how the clients should transmit uplink. Now the AP may send a trigger frame variant, the multi-user RTS, as we saw with the downlink, and it's going to, of course, solicit uplink CTSs, And that's if it's needed. We may not need the RTS CTS, but it may decide that it wants to do that for whatever reason, either full time or only as needed. Okay. And then we're going to send a trigger frame, and that trigger frame is going to assign the RUs and the time syncing, and then the uplink data comes on the RUs and followed by a multi-user block back downlink to the clients. The efficiency of the BSR, Buffer Status Report process, is an important one. We mentioned on the last slide that the uplink data transmission time for each of the clients must be the same. So when assigning this amount of time or for transmission to the clients, the AP has to decide on how long will that be, because of course some stations don't have very much to send, and we wouldn't want those stations having to pad a lot. So there's a trade-off here. If we shorten the time down, it gets inefficient. If we lengthen it out, stations are eating battery by transmitting pads that they really shouldn't have to be sending. So there's a big trade-off here of client for uplink transmissions of client battery burn versus throughput and efficiency across all the stations in a group. Another issue here is that if there's no station buffer data that the AP can use, in other words, it queries the station doesn't give it anything, or it simply doesn't query the stations with the report polls, then it has no idea of how to assign the RUs. And so those RUs are then assigned to be random access. Now this can cause clients to compete with each other on the RUs. If they just suddenly, if they're not told to be on this RU or that RU, then they may just choose an RU, a certain width, a certain position across the channel, and that may cause collisions. So we certainly want, for uplink transmissions, we certainly want the AP to be able to assign very specifically the RUs for each station rather than leaving them as random access, which can cause really bad inefficiencies. So the more sparse the network is, the less clients it has active. If we're using random access, the more of the RUs are going to be empty, and that's not very efficient. It's not using the channel very well. And the denser the network, the more collisions are going to occur if you're assigning these RUs as random access, because you have more clients trying to get onto various RUs. So it's always going to be better that the stations are queried with BSRPs and offer the BSR back to the access point so that they can be assigned carefully and optimally for efficiency purposes. Now, when stations wish to transmit using random access RUs or RUs that are assigned by the AP as random access because it didn't know how to assign them, they're going to use a special OFDMA backoff procedure that's a little beyond the scope of this presentation. Another feature that adds efficiency in 11AX is the Multi-TID A-MPDU scenario. In previous PHYs, 11AC and previous, all the way back to 11N, we had certainly have the ability to send aggregate MPDUs or MAC protocol data units where we are aggregating entire frames into one PPDU. One of the limitations that we've had is that each of the MPDUs had to have the same QoS level or same access category. But now with 11AX, we have the ability to change this, and we can combine voice, video, data, and so on, the best effort and background traffic categories into AMPDUs. So it allows scheduling at the access point and clients to be more efficient. Being able to send longer frames, not having to hold back one type of traffic while waiting on aggregating another, and so on. 11AX does allow for 20 megahertz channel width only clients. So this is ideal for IoT clients, as you can imagine, where they shouldn't be trying to use 40s and 80s. And when I say 20, I don't mean it's assigned to 242 only, 242 tone only. I mean that it's no wider than 20 megahertz width is allowed for the clients, all that it supports. So we'll see on the next slide how that will look visually. But this is optimal for devices that have small batteries that need to last a long time. And of course, a lot of these IoT devices are not going to have a full complement of 11AX features either. This is going to allow client manufacturers to design, less complex chipsets, lower cost, and this is going to be perfect for your standard IoT stuff. Now here you can see what this looks like when it's 20 megahertz only. We've got a 40 megahertz wide channel from top to bottom. And you can see that whether it be 26 or 52 or 106 or what have you, these clients can never be assigned anything greater than a 242 tone, and probably would normally be assigned, since they're IoT and their buffer depths would be very simple, very small, would be assigned a 26 tone all the time. But the key here is that the client's never going to use anything larger than a 242 tone, which of course is going to make it simple to design the chipsets, lower power consumption, and so on. You can see that client 6 here is designated as a 20 megahertz only client, and you can see across the top on the primary channel, the primary 20, it's staying within that 20. It's never venturing over into a 40 megahertz wide channel. Well, that ends video 2, and we hope you join us. I hope you enjoyed this, and hope you join us for the next video. Video 3, where we'll be discussing additional 11AX enhancements and 11AX throughput. Thank you.